Hi. Hey, it's Miss Murphy. So good to see you. Um, let's see. We're gonna photoelectron photoelectron spectroscopy. Okay. Big word, simple. I'm sure you could make it hard, but we don't need to do that. So I'm going to go here, share, go here. There's a little process for all this. Go here, share, share. Sorry, I have to go through the process. I haven't figured out how not to yet. Okay. Man, why does it make it so small? That's bothering me. Okay. So, photoelectron spectroscopy. All right. And you could see why it is spectroscopy. And I'm going to try to get this out of my way for now. Referred to as PES. Okay. You could see why. All right. What is photoelectron spectroscopy? It is like an experiment used to measure the energies of electrons. All right. Why would we have an experiment used to determine energies of electrons? Because that can give us insight as to where they're located, which could give us insight to the electron configuration, which could give us insight into properties of these elements or why certain elements react in certain ways and have certain properties, and it makes us more knowledgeable about our world. Okay, so what you need to realize is, let's see, electrons that are electrons closer to the nucleus. Let's start like that. Electrons closer to the nucleus have a greater binding energy. Right? And we could say that. What is binding energy? Well, what do you do when you bind things? You put them together. So when you could see that maybe is the energy released when the electron gets put there, or the energy that would have to be put in to the electron in order to remove it, right? So if this is our nucleus, and it's really important that you realize and consider that this nucleus is positively charged, right? It's not just random information. It's really important. And we know that the electrons are located on energy levels, right? They're not really like this, but it won't hinder it is my, anyone of my intellect to visualize it this way. It doesn't hinder my thought process, but your thought process might be more advanced than mine. Anyhow, should be 7. We don't need to worry about all that. What is important is that that nucleus is positive and that our electrons are negative, right? And I don't know if we've had the video. I think I made it and it got lost, and I have to make it again, of Coulomb's law. All right, we're going to reference this a lot in the next few lessons. Basically, it discusses the fact of the attraction between charged particles. All right, so we're talking about the attraction between positives and negatives, okay? And what we know that is, as the distance between these particles goes down, the attraction goes up. And that makes sense, right? We also know, according to Coulomb's law, is that as the charge goes up, well, then the attraction also goes up, right? Because something that has a greater positive charge would have a greater attraction for something that's negative. Or we could say that the negative particle would be more greatly attracted to the more positive charge, right? It's attracted to positive things. The more positive, the greater the attraction. Okay. Now, that's why those electrons don't fly off, right? Otherwise, they would be flying off into space because they would be repelling each other. Because we know that opposites do not attract. Opposites do attract, but we know that like charges do not attract. Now, I'm not being specific here with how many electrons are where, okay? So I'm not gonna, don't call me out on that and start counting my electrons. I'm just kind of doodling. Now, so what you should see here, we were talking about binding energy, right? And this is a main factor of what we're going to see here. And I'm going a long ways around this. I want you to understand, okay? But that binding energy is a main factor. So obviously, I think you probably already foresee where I would be going here. The closer the electrons, right? The closer electrons have a greater binding energy, right? Why? Because they're closer. And according to Coulomb's law, the closer the charged particles are together to each other, the greater the attraction. Now, I want you to listen to what Miss Murphy said. I said that the closer this electron will have a greater binding energy. And then I explained why. Because, and I say, listen to Miss Murphy, because you are going to have to explain the same things to me or the people reading your AP Chem exam. So you need to listen to the words, and let me see if I can find them again. Sometimes it's hard to find good words to explain things, and you have to learn to do this. This is the hardest part of the next few lessons, is you figuring out how to use the right words in the right way. Okay, so I said that simple, right? The electron closest to the nucleus has a greater binding energy. Now's where you want to listen. You probably want to write this down, because this is my explanation. Because according to Coulomb's law, as the distance between the electron and the proton decreases, the attraction between the electron and the proton increases. And that is why we have a greater binding energy for the first electron. It's so important that you can put that in your words. Steal my words, memorize them. You can use them. You don't have to copyright me, okay? You have to be able to explain Coulomb's law. You are not allowed to simply reference Coulomb's law by, according to Coulomb's law, it's got a greater binding energy. No, according to what about Coulomb's law? All right, that's going to be the hard part for some of you, and that's where you're going to find yourself losing your points, is your incorrect explanations. All right, okay. Now, and that's easy. We can elaborate on that a little bit more, and we'll be about done here. We'll just start looking at some PES spectrums. You're right. This one is further away. This electron is further away. The distance is greater. Further away. Lesser binding energy. Think of that energy as how strongly they are attached to each other, right? And you have to add, in order to unattach them, you would have to add the binding energy. You'd have to use that much energy to get them apart. You know, maybe picture yourself pulling a Band-Aid off of you, right? The stronger the binding energy, the harder it is to get that Band-Aid off of you, away from you. Same idea is occurring here. Okay. Now, what else should I tell you? I'm not sure, but I do have this resource that I'm going to pull up. Oops, right here. And you don't see it, I just realized. That's okay. Huh, that's really unfortunate. But you know what I could do? I have to think about that. Is I'm gonna have to, all right. Oh my goodness gracious, you still can't see it. Y'all, I'm sharing my screen with the internet, but y'all can't see it. So never mind. So what is a PES spectrum going to look like? Well, it's going to look like a graph, right? And down here, you're going to have binding energy, okay? And on the, over here, you're going to have, it's just going to reference the numbers of electrons. Now, I would like to stop and let you know that sometimes, you know, what I like to do when I teach certain things is to kind of dumb it down. And I want you to realize that, because when I write numbers of electrons, when you're looking at like a regular photo emission, a PES spectrum, you're going to see more like something that says intensity. So I should have written that first. You're going to see something that says intensity. And what that really is the number of electrons. Okay. So I'm trying, if you see me working over here, this is what I was going to pull up on your screen. And now that I can't pull it up on your screen, I'm just going to kind of copy some of the things that I was wanting to show you, but now I'm drawing it. So I apologize for that, but I don't want to start all over. My to-do list is too big. Back to focus, Ms. Murphy. Okay, so binding energy down here, this x-axis, I'm back, okay, is going to read backwards, reads backwards. So, I'm sorry, I'm taking so long, such that, let's say I'm going to make up some values, 1,000, and you're going to have a big unit that could be like megajoules per mole or something like that. Okay, so that's 100,000 times bigger than a regular joule. So we got 1,000 megajoules per mole here, maybe like 100 here, maybe like 10 here, and maybe like 1 here. So the PES spectrum reads backwards, where the high number is closer to the where the X and the Y axis meet, okay? And what we would see is, let's see, I've never actually, oh, I have drawn one. It takes, you got to think real quick. Well, let me let you see what I'm drawing. 1s2, 2s2. This is perfect, Miss Murphy. This is the perfect way to kind of detail this. And then let's make this 3p3. Actually, we could make that. No, that's good. Now, what we would also need to do here, guys, is extend this line, okay? And to be honest with you, let's just not have a scale, because I don't really want to worry about it. Now, right here, this is me thinking, this is the closest to the nucleus, right? Therefore, greatest binding energy. Right, and we'll just write BE for binding energy. And this would be the furthest, okay? Now we can learn a lot from this right here. Now, so we've already said that over here is where we are going to have the greatest binding energy, right? The greatest binding energy is here, right? This area here, greatest binding energy. We're going to call that BE, right? So we're going to put, just changing the color there, guys. We're going to put 2 electrons on this first energy level. Now, I'm going to give these 2 electrons, I'm going to make them real close to the, consider this like it's not, okay? but you can think of this as being the nucleus, right? You can almost think of this line right here being the nucleus, so that those 1s2 electrons are definitely closest to the nucleus. The height, well, we'll do that. Let's just move on to our 2s2 electrons. Well, they're gonna go from the first energy level to the second. So they are now further away from the nucleus. So the binding energy is less. There are 2 electrons there. So the height is exactly the same. And what you just learned was that the height references the numbers of electrons, right? Intensity. And Miss Murphy kind of just said, hey guys, all that means is number of electrons. But you're going to read intensity because it's fancier that way, right? Okay, now we're on the second energy level. So that's going to be close to this line because we're still on the second energy level. However, it is true that the 2p orbitals do, listen to my words again, this is another one of those, listen, the 2p orbitals do not penetrate as close to the nucleus as the 2s orbitals. And because they are not quite as close, they don't have quite as much binding energy. So they will be slightly over. And there will be 6 electrons, so it'll be 3 times the height of the previous 2. But notice how close these are together. This is my 2s, this is my 2p, this is actually my 1s, right? Okay, hopefully you're starting to see what's going on. Remember when I started, I said it's actually very easy? It is. Okay, but you know, you can take this and turn it into other concepts. So be careful, 2p, 3s. Well, we're now on the third energy level. So we're definitely going to have a less binding energy because every time we go to a higher energy level, we get further away from the nucleus. So let's go way out here. We're going to be the 3s. There'll be 2 electrons there. So we only need to go to about right there. All right. Let's continue color coding this. That's that. And now we'll go to the 3p. Now, remember that the 3p is still on that third energy level, so we're going to be very close proximity here. But it does not penetrate quite as close to the nucleus as the 3s, as the s orbitals. So it's a little bit less binding energy. Now, notice we have a 3p3. So this references about 2 electrons, right? This is supposed to be 3 times as tall. Maybe I didn't make it quite as tall as I should have. So this 3p, which should be 3 electrons, is going to go 1, 2, and then maybe we'll give it another 3, right? And that would be our PES spectrum. Oops, don't do that, Miss Murphy. And who would this PES spectrum, oops, we want a different color. This PES spectrum would be for, it looks like it would be for nitrogen. Oh, shoot. Let's go ahead and put that there, and then we'll draw it, right? Sorry, guys. It would be for nitrogen, okay? Now, when I look at this PES spectrum, and it is not labeled, right? Why don't we draw another one, guys? We'll make it quick. Let's go, right? What is this? This is binding energy, and this is intensity. This is always going to be my 1s, 2s. Oops, what did I do wrong? That 2s should probably, I don't know, just because I'm detailing it, I want to make sure to I want to make sure that you realize that we've jumped to a higher energy level, so we're further away. And then that 2p will be close, right? But this time we're not going to label it. We can, well, Sure, let's label it 1s, 2s, 2p, 6, and then we come out to 3s, and then we could go 3p4. Okay, now, what kinds of questions could you have? You could have, what element is this? Right? What element is this? And you would be expected to realize, and they would, if it was for points, you know, they would somehow allow you to realize that this was a third of this, right? So we tried to go to 3p4 was my attempt. There, that helps. Oops, I don't want to undo. So what other questions could you see? You could see, you know, why is the 3s so close to 3p, right? Or why is the 2s closer than 3s? You know, I mean, they could be like really, really simple questions, but you'll be surprised at how many students will actually miss them because they don't see how, you know, they're not paying attention to realizing how simple this is. You could, you know, be asked, like we had in the warm-up yesterday, about ionic charges, or, you know, ionic compounds in terms of the ratio of the ions. So we would see here that this guy has 6 valence. Anyone with 6 valence is in oxygen's group, right? That's oxygen's group. And oxygen's group has 2 negative charge, right? So when I went to remove those 2 electrons, actually, that's not removing electrons, Miss Murphy, that's adding electrons, right? They would go right here, right? If I wanted to remove an electron, I would always remove the valence electrons first. I can't think of anything else that you really would need to know. I'm kind of looking at this graph right now. Yeah, that's it. If you followed along there, that's pretty much it. I could also leave it at that. Okay. Let's see, what do? I stop share. Bye, guys. See you later.